All right, everyone, welcome to part 2 of today's lecture. We're going to start looking at binomial probability. You might say, what is binomial probability? Well, first thing I would sort of clue you towards is the prefix in binomial being bi, meaning two, right? Think like bicycles. Binomial probability is anything that can be defined as successes and failures. For instance, if I'm flipping a coin and I want to get a heads, well, heads on the result would be a success and tails would be a failure. Only two possibilities, it's a binomial probability. Okay? If I'm rolling dice and I'd say that a 6 is a success and every other number is a failure, even though they're not the same percentage, right? A 1 out of 6 versus a 5 out of 6, they're still just successes and failures and therefore a binomial probability. So a Bernoulli trial is essentially a bunch of binomial probabilities done in a row where the value and the chances don't change. So for instance, the thing I mentioned a moment ago, right? If I'm rolling a d6, let's say 100 times, I'm going to define getting a 6 as my success and probability of getting anything else, some other value, as a failure. Well, I'm doing it a bunch of times. I define it as just success and just as failure. And as we know, if I roll a d6, no matter how many times I get a 6 or I get a 4 or any other number, it doesn't affect what's going to happen on the next roll. This would be a set of Bernoulli's trials. If we go back for a few moments ago, we were looking at that jar without replacement. Well, let's make it a little bigger. Let's say my jar now has 400 red balls, 300 blue balls, and 100 green balls. I can still define things similarly. I can say the probability of getting a red is my success. I can say the probability of either a blue or a green is my failure, but what's different here is that I said specifically without replacement. So every time I draw a ball, there's one less in my draw. So the first time, for instance, 400 out of 700 being my success possibility of getting a red. But on my second one, now it's down to 399 over 699. Because it has no replacement, it's changing my possibilities, not a Bernoulli trial. So the key thing here is that the probability of a success must remain the same or remain constant. All right. So let's take a look at an example of something that we could put into a set of Bernoulli trials. We'll consider this spinner, numbered 1 through 3. We're going to call the number 2, the green part, a success, and the 1 and the 3 a failure. All right. Let's take a look at the full set of possibilities. Well, I could get a 1 and a 1, and I could get a 1 and a 2, and I could get a 1 and a 3. I could also gain a 2 and a 1, a 2 and a 2, and a 2 and a 3. Last but certainly not least, we could get a 3 and a 1, a 3 and a 2, or a 3 and 3. So that's our full set of what could happen. If I say that x is what we call a random variable, meaning just the variable that describes the number of successes of something, in this case we're going to say that our x is number of successes. Well, how many ways can I get the probability of x being 0, of no successes? Well, let's see. I have a non-success here, and here, another one here, and another one here. Right? These are all zeros. So there are a total of 4 out of 9 ways to get no successes or no 2s on the spinner. I could get one success, right? Well, I have 1 here. I have a single 2 there, a single 2 here, a single 2 here, and another one here, or another 4 out of 9. We'll go with green for the full successes. How many possibilities of getting 2 of them? Well, that's my only chance here, 1 out of 9. Now, whenever you have a setup where you can sort of pull out all of the possibilities of a Bernoulli trial, or a set of Bernoulli trials, we call that a binomial probability distribution. The idea being that we're showing the full distribution of everything possible from that set of trials. A couple of key things here. First and foremost, again, it must be a Bernoulli trial for this to be a binomial probability distribution. And more importantly than that, we want to make sure that with all of our trials, in order for them to truly be the full distribution, we need to make sure that they all add up to 9. So 4/9 for the first piece, 4/9 for the second piece, 1/9 for the third is 9 out of 9, or 1, aka 100%. Now, we went through some work here. We had to write out a whole bunch of stuff and kind of count them all up to find our trial pieces here. And you can imagine that if I said, hey, instead of spinning the spinner twice, what if I said spin it 300 times? Well, this becomes a less pleasant problem really quickly, right? I don't know about you guys, but I don't have the time to write out 300 possibilities with 3 sets apiece, which is why mathematicians years ago came up with what's called the binomial probability formula. All right. Now, there's a lot of numbers and letters here, but it's actually not that bad. A couple of key pieces of information. So if we have n independent events, in other words, however many of them we're doing, so if it's 2 spins, for instance, the n would be 2. If it's 300 spins, our n would be n. Where the p is the probability of success. In our example, right, 1/3 was the chance of success. And q is the failure. 2 out of 3 were possibility. Okay. We know that x is the number of successes we're looking for. We can just apply this formula. Okay. Now, I know that you see this thing here, but really, all that is, right, q being 1 minus p is just another description of the probability of a failure, right? 1 being 100%, p being successes, 1 minus the successes, like when we talked about complements, would be the failures. And again, this formula looks a little rougher than it is, but some of it should look familiar. For instance, we see that we have an n factorial over x factorial times n minus x factorial. Well, we know from earlier in the chapter that just really means combination, right? So essentially, if we take the combination and we multiply it by the successes and the failures with specific coefficients, exponents, we can find our probability. Let's try applying that to the problem we just looked at a moment ago. So instead of writing this all out, if I wanted to just calculate the chances of getting a 0 number of 2s, I could approach this from the binomial probability formula, right? I could say that n, my number of trials, was 2. Now, the probability of success, my p, well, if I'm looking at my spinner, right, there are 3 equal shots. One of them is a 2. There's a 1/3 chance of getting a successful spin. And by the same logic, 1 minus p, or 1 minus 1/3, gives me 2/3 of a chance to get an unsuccessful spin, a failure. And that makes sense because I see 2 possibilities out of the 3 that would not work. Now, since I'm doing x equals 0, the 0 number of successes, well, I want 0 successes, so that's my x. And now I can simply plug it into my formula. So I have ncx times p to the x times q the n minus x. Well, that literally means n2 chooses 0 times my 1/3, which is my p, my probability of success to the 0th power, times my failures, 2/3, to the n minus x, which is 2 minus 0 in this case. Which, if you plug it into a calculator, you'll see that it comes out to 4/9. Why? Well, 2 choose 0 is 1. There's one way to choose nothing out of 2 things. Anything to the 0th power is also 1. And we're dealing with 2/3, the 2nd power. Well, whenever we do a fraction to an exponent, it's kind of like distributing the exponent to both the top and the bottom. 2 to the 2nd is 4. 3 to the 2nd is 9. As you might notice, ding, 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 we got the same value. Now, again, for this problem, it might be easier to just list them out if you're not comfortable with the formula, but as things get more complicated, it really does save us quite a bit of time. Let's take a look at a few examples. So let's talk about finding the probability of obtaining exactly 3 heads in 5 tosses of a fair coin. When I go to deal with these problems, the first thing I do is I set up all of my variables. I know I'm going to need the number of trials, the successes, the failures, and the number of times that it needs to succeed for my problem to function. Okay, so here it says there are going to be 5 tosses, so that's my n. Chances of getting a success on a coin, assuming it's a fair coin, which we are told that, is 1/2, and therefore the chance of a failure is also 1/2. And we said we wanted exactly 3 heads, so x is equal to 3. And now we can plug it in. 5 choose 3 times 1/2 to the 3rd power times 1/2 to the 5 minus 3, right? We're just applying that formula, right? NCX times P to the X times Q to the N minus X. And if we plug that into a calculator, well, let's take a look. 5C3 came out to 10 times 1/2 to the 3rd. Well, 1 to the 3rd is 1. 2 to the 3rd is 8. Times 1/2 to the 5 minus 3, right, is just 2. So 1 to the 2nd power is 1, 2 to the 2nd power is 4. We multiply across. Quick reminder, there's always a hidden 1 under an integer, right? So 10 times 1 times 1 is 10 over 32. We can reduce that by 2, bring it down to 5 over 16. And of course, if you're more comfortable, you can just plug that into your scientific calculator. I assure you that's how I got the combination. So again, N, P, Q, and X. Number of trials, probability of success, probability of failure, and the number of successes you want in your set. Let's do another one. Find the probability of obtaining exactly 2 6s in 6 rolls of a fair die. Well, again, N, P, Q, and X. I am doing 6 rolls of the die here, so N is 6. I want 3s. Well, on a 6-sided die, which is what we were to assume here, there's a 1/6 chance of getting a 3. If there's a 1/6 chance of getting success, that means there's a 5/6 chance of not getting that number. And I'm looking for 2 of them, so my X will be 2. Again, NCX times P to the X times Q to the N minus X. Now we'll plug it all in. 6 chooses 2 times 1/6 to the 2nd times 5/6 to the 6 minus 2. My handy dandy scientific calculator tells me that 6 choosing 2 is 15. 1/6 squared is going to be 1 over 36. Again, squaring both the top and the bottom. Over here, 6 times minus 2 is 4. And let me just do a quick little math. 5 to the 4th is 625. 6 to the 4th. Oop, that again, 6 to the 4th is going to be 1296. Multiply them across. And what we should get on the top, 15 times 625, should be 9375, divided by 36 times 1296, giving us 46,656. This will then reduce down to 3,125 on the top over 15,552 on the bottom, which comes out to a 0.201 or a roughly 20% chance. Let's keep going. Find the probability of obtaining less than 2 3s in 6 rolls. Well, if I'm looking for less than 2 3s, that means I have some possibilities here, right? Again, still the same idea. We're going to go N, P, Q, and X. But here, right, our N will still be 6. Probability of getting less than 2 3s. Well, our probability of success there is still 1 out of 6. Our failure is still 5 out of 6, but this time, right, instead of it just being x equal to 2, it's x is less than 2. Well, what does that mean? Well, it means I could either get 0 or 1 3s. All right, well, how do I do that? Well, just like before, I'm going to find my probability of getting 0. It's still n cx times p to the x times q to the n minus x. And then I'm going to add on the possibility of getting 1, which will be another n cx p to the x q to the n minus x. So if I'm looking for 0 first, I have 6 choosing 0 times 1/6 to the 0th power times 5/6 to the 6 minus 0 power. On the second side, well, now I want the 1s. 6 choose 1 times 1/6 to the first times 5/6 to the 6 minus 1, or 5, right? So if I work these all out in my calculator, I'm going to get 0.3349 for my possibility of getting no 3s. For my possibility of getting 1 3, I'll get 0.4019, giving me a total possibility of 0.7368, right? And again, really these are plugged into your calculator. Let them find the values for you. The important idea is how to apply the formula, right? Number of trials, probability of success, probability of a failure, and how many successes you want. If it's a less than, there were 2 possibilities, 0 or 1. Let's take a look at a baseball player. So it says a baseball player has a well-established batting average of .250. In the next series, he will bat 10 times. Find the probability he will get more than 2 hits. Now, just like before, we have more possibilities, but this one could be a little scary if we weren't careful, right? If I want the probability of getting more than 2 hits, if I were thinking mechanically, I might say, all right, well, I've got to figure out the probability of 3, 4, 5, 6, 7, 8, 9, and 10. But if I think a little bit, I also know that by the complement concepts earlier in the chapter, that's the same as the probability of 1 minus getting less than or equal to 2 hits, right? Meaning I really only have to calculate the values for 0, 1, and 2. Because if I find the probability of getting 2 or less hits and subtract from the probability of getting all of them, that'll leave me with everything over greater than 2. So let's go ahead and calculate it all out. This whole thing, well, if I want the probability of 0, that'll be 10 choose 0. Now our probability of getting it is 0.25, we're told, the 0th power. If our probability of getting a hit, the success is 0.25, that means our failure is 1 minus that, or 0.75, to the 10 minus 0. That's possibility of getting 0 hits. We also need to figure out the probability of getting 1 hit. So 10 choose 1. Again, success probability is 0.25 to the first. Has the probability of a failure, 0.75 to the 10 minus 1, or 9. And then last but certainly not least, probability of getting, not 0 hits, but 2 hits, because we do need less than or equal to 2, giving us 10 choose 2 times the probability of a success, the number of successes, times the probability of a failure, the total number of trials minus the number of successes. And I want to take that whole value, because those are the chances of me getting a 0, 1, or 2, something less than or equal to 2, and I want to subtract it from 1, just like we wrote our formula up here. So, again, if we use a little bit of calculator magic here, chances of getting a 0 when you plug it in are 0.0563. Chances of getting just 1 are 0.1 0.877. A little bigger so you can see it. And the possibility of getting 2 is 0.2816. Add them all up and subtract. We get a chance of getting at least 2 hits of 0.474. All right. So those are just a few applications of the binomial probability formula. I look forward to seeing you all on Thursday. The homework is currently posted. Thank you so much for your time and have a great day.